And that was The Heat Goes On, and so do the heat notes. On and on and on. All right, welcome to part 3 of the heat notes. All right, let's get going. Okay, we had left off at talking about heat. Heat is when energy flows from high temperatures to lower temperatures, and heat is that flow of energy, that whole flow of thermal energy. All right, and it always goes from hotter to colder. Now, it is measured in units called joules. All right, J for joules, or it can be measured in calories. Okay, either one are appropriate. They're just a little different from each other. A calorie is equal to 4.18 joules, technically a little bit more than that, but we rounded off to about like that. Okay, and so which one is bigger? Is a calorie bigger or is a joule bigger? Well, if it takes 4 joules to make 1 calorie, that means the calorie is bigger, just like it takes 4 quarters to make $1, so $1 is more money than a quarter is. Okay. Now, the question is exactly how big is a calorie? I'm glad you asked that question. It's a very good question. And here we go. So, if you had a die or dice, oh, sorry, those are fuzzy dice, not the right kind. Sorry, set those out. Let's get the other kind of dice down here. There we go. If we had a dice like that, or a die, if it's just one, and let's say that this die was 1 centimeter by 1 centimeter by 1 centimeter. That would be a cubic centimeter, or cc's, centimeters cubed. All right, that would be a fairly small amount of water, and the amount of heat that it would take to make it go up 1 degree would be a calorie. All right, so it is a fairly small amount of heat, even though it's bigger than a joule. Joules in are really small. A calorie is the amount of heat needed to raise the temperature of 1 gram or 1 cubic centimeter of water 1 degree. Okay, or a milliliter of water. If you think about a graduated cylinder, it has 100 milliliters. 1/100th of that would be a cubic centimeter of water. So it's fairly small. Now the problem is we also use heat to measure things like calories. In the food, when you look on the side, it says there's so many calories. Well, the problem was when we use this kind of calorie, one candy bar, for example, might have 222,371 calories. Well, counting calories is hard enough, but with big numbers like that, it's just almost impossible. And so they said, hey, let's just make a different type of calorie for food, okay, because it's going to be a lot more energy than some of these other measurements we're doing. And so they came up with what we call a food calorie. Sometimes it's a capital C calorie, but obviously if the little c is at the first of the sentence, that gets confusing. So we're just going to call them food calories. Okay, a food calorie is actually 1,000 calories or 1 kilocalorie. Another way to look at that is that if you took this cubic centimeter of water and made the temperature go up 1,000 degrees, that would be a kilocalorie. Or another way to look at it, if you had a big beaker full of 100,000 milliliters of water, then the amount of water it would take to make that whole thing go up 1 degree, 1,000 milliliters or 1,000 cubic centimeters of water to go up 1 degree would be a kilocalorie. And this is the kind of food we use to measure our food with, because it just takes a whole lot more. All right. So just for the record, if you did a kilocalorie, it would be equal to 4,186 or whatever joules. All right. So those are calories and joules. Both of those can be used to measure heat. Now, while we're also talking about heat, the question is, what is cold? Cold is just the absence of heat. Cold is not a thing, it's a lack of something, in this case heat. In other words, if you go outside and you get cold, it's not because cold moves into your body, it's because heat moves out of your body. So when you go outside, the heat from your body is going out. All right? Therefore, you become cold. Now, someone says, but when you have a wind, that wind cuts into you and cold goes into your body. But no, what happens is, since your body's constantly trying to warm up the air around it. Looks like Dr. Octopus there, but okay. It's trying to warm up the air. If you have wind, it's constantly moving that air out and moving cold air back in, and so you're constantly trying to warm up that cold air right next to you, and that's why you get a lot colder on a windy day than you do on a day that's not very windy. Okay? a coat, when we put a coat on around our body here, okay, it traps the air. Once we warm up the air around us to a certain temperature, then we quit losing heat, and therefore the coat keeps us warm. What it really does, it keeps our heat in, and so that we don't have to warm up any more of the air around us anymore. So cold is just the absence of heat. It is not a thing, it's an absence of a thing. Kind of like dark is the absence of light. Okay, so if there's no light, it's dark. And if there's an absence of heat, it is cold. All right, so that's basically all cold is. Now, next we're going to talk about the phases of matter. If you're in a room right now, the odds are that there are some things that are solids, some things that are liquids, and some things that are gases. And yet, they're all in the same room. What determines whether something is a solid, liquid, or gas at a certain point? And it just has to do with the atoms. In a solid, we said the atoms are held close together. They're tied to each other. All they can do is kind of vibrate in place. Okay? And so they have very strong bonds, sometimes called ionic bonds, positive and negative bonds, that hold them together. Okay? And because these forces hold them together, they are called the intermolecular forces. Okay? That's a big fancy word. All it means is the force between molecules. Okay? If there are strong intermolecular forces that really hold them together good, like say between two iron atoms, okay, in that case they are going to have a high melting point. It's going to take a lot of energy to break them loose, and so they can start sliding around each other inside the liquid. So things are, if they melt, then they can start moving around. And so it's going to take a high thermal energy, lots of energy to break that loose, because they have these strong forces holding them together. All right. As they get weaker forces, then those substances may already be a liquid at room temperature. Say water, for example. Okay, they have forces between them, but they're not as strong, and so they would usually be a liquid at room temperature. On the other hand, gases, very often, which are two of the same atom joined together, and they don't have a very strong charge between them to hold them together, and so gases tend to be just floating around on their own all the time anyhow. Okay, they break loose and the atoms are just floating around, bouncing all over the place, because they don't hold themselves together very good. All right, and so they have what we call weak intermolecular forces. Intermolecular forces, which means they don't hold the atoms together very good. So they have low melting points and low boiling points. And so usually by room temperature, they're already boiled, if you will, and they've turned into gases. All right. We could have also said for strong intermolecular, they're also going to have high boiling points. A piece of metal, for example, might have to get up to 1,000 or more degrees in order for them to actually turn to a gas. But theoretically, you could heat a piece of metal up to the point that it would become a gas. All right. Now, akin to this idea of molecular forces, also, there's another concept of how well do they absorb heat, okay, and therefore make their temperature go up. And this is called the specific heat, as opposed to generic heat, I suppose. Anyhow, also as opposed to the Atlantic heat. Actually, the only heat on the Atlantic would be the Miami heat, and they're not playing right now anyhow. So let's talk about specific heat. All right, specific heat, the symbol for specific heat is very logically CP. Don't ask. All right, I don't know. But CP is the symbol for specific heat. All right, I suppose all the other S and H symbols were already taken. I don't know. And basically, it is the amount of heat that it takes to raise the temperature of 1 gram of a material 1 degree Celsius, or it could be a kilogram. Sometimes they measure kilograms, so obviously it's going to be a bigger answer then, about 1,000 times more. The specific heat of water would be 1 calorie per degree Celsius, all right, for gram degree Celsius, sorry. All right, so what that means is, we said the specific heat of water is 1 calorie per gram times degree Celsius. Okay, and so that would be the specific heat. Now, it could also be written in joules, and remember 4.18 joules are equal to a calorie, so it would be joules times grams times degrees Celsius. Okay, but either way, both of those would tell us the same information. In other words, how much heat energy does it make for 1 gram of the substance to go up 1 degree Celsius? All right. If it was 1,000 or kilogram, that would be like a kilocalorie. It would be 1,000 calories per kilogram times degree Celsius, because there's 1,000 grams, so there's going to be 1,000 calories. It's going to increase the amount that much. But usually we're going to use probably joules over grams degree Celsius, or calories over gram degree Celsius. All right. Now, so basically it's the amount of heat it takes to rise the temperature 1 degree. All right. Basically, if something has a high specific heat, which water does, for example, it's going to take a lot of thermal energy, a lot of heat, to make the temperature go up 1 degree Celsius. If you ever sat around waiting for water to boil, you know it's like it takes a long time for the temperature to go up to get high to boiling, okay? Especially once it gets close to boiling. All right. It also means that it has to lose a lot of thermal energy. That's an F there. Thermal energy to make the temperature go down. Okay. Now, both of these mean, one, water heats up slowly, and it means it cools down slowly. And that's important to us because our bodies are made out of water, which means if we go out in the sun, we don't heat up real fast and we don't cool down real fast in the cold weather, so we can keep a steady body temperature. If we had a low specific heat, okay, it means it takes a small amount of thermal energy to make the temperature go up 1 degree, or it would have to lose a small amount of thermal energy to make the temperature go down. Okay, metals would be a good example. Metals heat up very quickly. If you put that's why we use pans made out of metal. We stick it on the stove, the heat goes up very quickly, so it can transfer that heat to the food. Okay, but on the other hand, for example, if you are grilling something and you've got tinfoil wrapped around it, as long as it's touching the meat or whatever, it will get very hot and it will transfer that heat to you very quickly. But once you if you peel it off where it's not touching the meat, it will cool off very quickly as well, and then you can pick it up by the little tabs of tinfoil on the ends. So water, which has a high specific heat, heats up slowly, cools down slowly. Metal, on the other hand, has a low specific heat, and it will heat up very quickly, but it will also cool down fairly quickly. All right, last thing in this video, we want to wrap up really quickly, has to do with Q, or calculating changes in thermal energy. Q is just the change in thermal energy. Okay, how much does it change? All right, and the formula for that is you take the mass of the substance times the change in temperature, which is the final temperature minus the initial temperature. How much does the temperature change? But it's always final minus initial, times the specific heat of the substance, whatever it would be. Okay, and different substances have, as we said, different specific heats. All right, if you look at the problem in your notes, it says you have a silver spoon that has a 32 grams, all right, and the heat changes from 21 to 61. So is it heating up or slowing or cooling down? It's heating up, that's correct. So it's going to be your final temperature, 61 minus 21 degrees Celsius, okay, and it's going to be times the specific heat of silver, which is 275 joules. So if you will calculate that, I hate to leave you in suspense, but you'll have to tune in to the next note, part 4, and find the thrilling conclusion to that question. I will see you on the flip side.